Good morning and welcome to the webinar on vibration analysis of machine element, in which initially we'll have some theoretical background of the basics of vibration and then go on to the demonstration of solving the vibration problem using ANSYS Workbench. Just to give an introduction about the mechanical vibration, as we all know that it is a study of oscillatory motion of the bodies. Vibration occurs in all bodies which possess mass and elasticity. Now, they are caused due to several reasons, such as the elastic nature of the system, which is the inherent property. Or vibrations are also caused due to the natural cause like wind, low, tidal waves, and earthquakes. Vibrations are also caused due to the man-made cause, which may due to the presence of unbalanced force in the machines or in the part, or by the application of the external forces. So the vibration is usually defined as a motion which repeats after equal interval of time and is also a periodic motion. That means motion will be repeating itself after a certain duration of time, which we call it as the time period of motion. Vibrations are harmful or undesirable for engineering system as they induce high stresses in the system component, leading to the noise and failure. But here we are not discussing about the desirable effect of vibration, because desirable effect are having more advantage, which we are not touching upon. It is only on the undesirable effect which causes the effect on the human being is what is going to be discussed about. The vibrations which are undesirable and harmful are to be minimized, if not totally eliminated. Excessive vibration causes discomfort to human beings, damage to the buildings and machines, and wearing out of the machine parts due to this vibration. Thus, an understanding of the basic fundamentals of vibration analysis are very much important in forming or in developing a solid background to analyze the problem of machine elements in the design and see that the vibrations are reduced to the extent, to the limit what is exactly required. So the main cause of vibrations are the bad design. If the design is bad, then due to that, the vibrations are maybe induced. That is, when you are designing, if the masses are not being treated appropriately, and if these masses are unbalanced, these unbalanced inertia forces will cause vibration. And also in the poor quality of the manufacturing. So if the quality of manufacturing is not up to the required specifications due to misalignments and due to the surface roughness and other things, vibrations may be caused. Then improper bearing. That is, if the bearings are not being appropriately mounted, or if the design of the bearing itself is not appropriate, or the mounting of the bearings, if it is not being aligned, there is a problem of passing the vibration. Then the worn out machine parts or components are the gear teeth. Due to the servicing conditions, if it is being used for a long period, there is a wear and tear in the machine parts, which in turn may cause vibration in the component. Or it may be causing due to the external excitation applied on the system. These external excitations may be of anything. It may be either in the form of the forces, or it may be in the form of displacement or acceleration or velocities. Now, the effects of vibrations are as follows. Due to this vibration, earlier failure due to the cyclic stress. That means since the motion is going to be repeated motion, and if the forces are going to be considered during this action of motion, The loading which is going to be is the fatigue loading and not the conventional type of loading. And all materials are being observed that the behavior of the material is going to be totally different when it is subjected to cyclic load when compared to the static load analysis. And due to this vibration, there may be an increase in the wear and tear of the parts. And due to this wear and tear, there may be excessive unwanted noise. And if these kind of parts are being incorporated in the machine which produce certain product, the product which is coming out of that particular machines may be of poor quality. So when these poor quality products are there, then they're difficult to sell the products. Thus, vibrations in machine tool can lead to improper manufacturing or machine the parts. Now, when you want to describe the complete behavior of any dynamic system, the complete description of the vibration problem is going to be involving mainly three components. And these components, which is going to be the system, the vibrating system, and then the external stimuli, or what we call it as the excitation. And then due to this excitation of the system is going to be responsive. So all machines are being broken into two specific categories, which is consisting of a mass and stiffness. So this mass is going to be representing an object which moves or which may rotate, that is, there is certain amount of displacement in it. Whereas the stiffness is represented by a spring or a resistance or a constraint of that movement. So the stiffness of the body is nothing but the internal resistance offered to the displacement is what we define as the stiffness. So the mass and stiffness are going to be playing the key role in the dynamic behavior of the system. To reduce the vibrations, there should be certain amount of instruments or some elements are to be incorporated to absorb the vibration energy, which you usually call it as a damping. So thus, every vibrating system in general compromises of three parameters, and these inverse, which includes the inertias due to the masses, and these masses due to the motion causing the inertia will be linked to the kinetic energy developed in the system. Whereas the internal resistance to the deformations, which we define it as the stiffness, which is going to be a link to the potential energy stored in the system. And then the external element which has been incorporated into the dynamic system to reduce the vibration amplitude, the damping, which indicates the energy that gets dissipated from the system during vibration. So these are the three major elements which we look at for completely describing the dynamic behavior of the system and see that which is causing the main idea for inducing the vibration, or if you want to reduce the vibration, how exactly the dampings are to be looked upon, and whether the mass or the stiffness either to be increased or decreased can all be looked in the design stage itself. So when we classify the vibration, there are different methods of classifying the mechanical vibration that are being completely based on the type of vibration, the degree of freedom, the displacement, and the behavior of the system. When we talk about the type of vibrations, whether it is a free vibration or a forced vibration, pure vibration which occurs due to the inherent properties of the system without any external disturbance, forced vibration are caused due to the external excitations. Now, whenever the system is completely vibrating due to its inherent property without any external forces and without any energy loss. So whenever there is no energy loss in the system, we call that to be as an undamped system. If there is any kind of energy loss, we call it as a damped system. Then depending on the degrees of freedom, we define the vibration as a single 2 degree or multi degrees of freedom. or it may be a continuous system with infinite degrees of freedom. So single, two, and multi degrees of freedom system are going to be consisting of rigid bodies, whereas any body which is a continuous, then we call that to be as a continuous system with infinite degree of freedom. Now, when a rigid body can be defined as a degree of freedom, which is depending on the number of independent coordinates required to define the equation of motion completely. That should be underlined. Independent coordinates and the equation of motion completely. So the number of independent coordinates required to define the equation of motion completely is defined as the degrees of freedom. Now, if you are able to describe the equation of motion by only a single coordinate system, you call it a single degree of freedom. If it requires two coordinate system, you call it as 2 degrees of freedom. Anything more than 2 degrees of freedom system, we call it as multi-degree of freedom system, in which the entire system is consisting of rigid bodies. Whereas if the body is going to be a continuum is going to be consisting to be made up of particles which has certain masses. And hence, if the continuous has infinite number of particles, then it is going to be under the study of infinite degrees of freedom. Now, based on the displacement, how it is going to be displacement, the vibrations is being classified as a longitudinal vibration, lateral vibration, or torsional vibration. So longitudinal vibration, whenever the displacement which passes along the axis of the system, longitudinal axis, that is in the direction of the forces or in the direction of the displacement, which we look at, then you call that to be as longitudinal vibration. If it is going to be displacing laterally, that means perpendicular to the longitudinal directions, we call it as lateral vibration. And if there is a twisting displacement or the rotational displacement, then we call that to be as torsional vibration. Then vibration is also classified under the behavior of the system, how exactly the entire system is going to be behaved, and how the equation of motions are going to be represented, whether it can be represented by a linear variables, then you call it as a linear vibrating system. Or if the equations are going to be non-linearly varying, we call it as non-linear varying system. Or if the equation is going to be, or the behavior is going to be for the sudden application of the loads which are acting for a short duration of time, we call that to be as transient response. And then if the external excitations are going to be random, and if the behavior of the system is also going to be random in nature, then we call that to be as random vibration. So in the transient response, it is going to be acting for a short duration of time. The system response decays back to its equilibrium position after a certain duration of time. Now, certain notations which are commonly used in the studying the dynamic system. It is a time period. It is the time required for one complete cycle or one to and fro motion. And the units of time is always taken in second. Then we have the frequency. It all depends upon whether it is translatory displacement or rotational displacement. It is a number of cycles per second. The units are cycles per second, or it's been defined as hertz if it is translatory motion. Or if it is circular motions, you call it as the circular frequency or the angular velocity omega or angular frequency omega has been defined in radians per second. Then we also define the displacement as amplitudes in dynamics. Now it is the displacement of the vibrating system from its equilibrium position. Its units of length is in general in millimeters or in meters. Then damping is a resistance offered to the motion of a vibrating body by absorbing the energy of vibrations. There may be different types of damping, which will be just looking on later on stage. Then the type of forces or the displacement which is being considered in the vibrations we call it as harmonic motion. So these oscillatory motion may repeat itself, which are following a certain mathematical law regularly. Now, when the motion is repeated in equal interval of time, it is called as a periodic motion. When it is following a certain mathematical law, you call that to be a harmonic motion. Now, here we consider a point which is moving at a constant angular velocity from a fixed point. The constant angular velocity is omega, and it traverses at a constant angular velocity. The path traced by the point P is what we define it as a simple harmonic motion. So here it follows certain mathematical laws such that as it rotates at an angular velocity, it has been observed that its acceleration is always directed towards its equilibrium. Its acceleration is always directed towards its equilibrium. So when the point is moving at an angular velocity omega at any given instant of time t, it occupies the position A, position P. And since OP is having the distance from the point of reference as A, the angle which it turns is given by theta, that is going to be omega t. Now the vertical distance which is traveled, y, can now be expressed as A sin omega t. Now, when you substitute the value of t, omega t for different time, we get the sinusoidal wave. And this is what which you call as simple harmonic motion. Now, here the quantity omega is generally measured in radians per second and is referred as angular velocity or the angular frequency or the circular frequency. If the motion is designated by a time function x of t, then any periodic motion must satisfy the relations x of t equal to x of t plus tau, where tau is the time period, that is the time taken for one complete oscillation. Now, simple harmonic motion, as shown in the figure in the previous slide, is often represented as the projection of a straight line of a point that is moving on a circle at a constant speed. That is at an angular velocity of a line OP designated by omega. Then the displacement x can be expressed as x of t equal to y sin omega t. Now, since the motion repeats itself, so for one complete revolution, it makes an angle of 360 degree, which is written as 2 pi radians. Then we have the relations, that is omega into tau is equal to 2 pi. Tau is going to be 2 pi by omega. Now 1 by tau, which is the thing that the number of cycles per unit time is defined as the frequency, which is the reciprocal of the time period, will now become omega by 2 pi. Thus, we see that omega is going to be either 2 pi by tau or 2 pi f, where tau is the time period in second or f is the frequency in cycle per second or hertz. So using this, one can easily determine what is going to be the time period and the frequency of the system. Now, we're using the dot notation for the derivatives with respect to time. So any variables, when it is having the derivative with respect to time in dynamics, we represent it by dot notation. And thus we see that x is the displacement which is expressed as A sin omega t, whereas the derivative of the displacement with respect to time is the velocity. That is, x dot is going to be equal to A sin cos omega t, which can also be expressed as A omega of sin omega t plus pi by 2. Then the second derivative of the displacement, which is nothing but the acceleration, which is been defined as x double dot, which is going to be equal to minus of a sine a omega square sine omega t. And this minus sign can be eliminated by replacing sine omega t as sine omega t plus pi. Now we see that sine omega t plus pi, which is nothing but again equal to the value of sine omega t, that is x, which is defined as a sine omega t. So thus here we observe that x double dot is also going to be equal to minus of omega square x. And thus we can express here that the acceleration is always directed towards its center and it is proportional to the displacement. And the constant of proportionality is what it is, minus of omega square. And thus, we write the equation as x double dot plus omega square x equal to 0. And this is the equation of motion for any simple harmonic motion, in which this equation is a second order differential equation, which is homogeneous differential equation, and has a standard solution given by x of t equal to a sin omega t plus b cos omega t, where a and b are the constants to be determined from the initial conditions. So in dynamics, the initial conditions which we usually consider is the displacement at time t equal to 0 or the velocity at time t equal to 0. So with these two initial conditions, one can extract the constants A and B and determine how exactly the displacement or the dynamic behavior of the system is going to be. This is the standard simple harmonic equation which is being used for the comparison of any dynamic system which is harmonically excited. Now, when the system is exciting, its frequency at which the body vibrates due to the inherent properties when it's subjected to any external disturbance are not allowed and without any energy loss. We call such a vibrating system as a free vibrating system. And the frequency at which this system vibrates, we call it as the natural frequency. So the natural frequency is an important aspect in the dynamic system for any further analysis which are being subjected to any other type of load, because this completely describes the behavior of the system without any external disturbances and external or energy loss. Then we have the fundamental mode of vibration, as we see a continuous system which will be having infinite degrees of freedom. Thus, in any vibrating system, may have more than one natural frequency. And when it is vibrating at its lowest natural frequency, and that is what which we call it as the fundamental mode of vibration. That is the first natural frequency of the system. The free vibration is that which takes place when a system oscillates under the action of inherent forces in the system itself, and when the external impressed force and the energy losses are absent. There is no energy loss and no external forces are acting. But for any slight disturbance, if the system starts to vibrate, and this vibration you call it as the free vibration of the system. Now the system under the free vibration will be vibrating at one or more of its frequency, which is called as the natural frequency, which is the property of the dynamic system established by its mass and stiffness alone, because there is no loss of energy. Damping does not interfere into this. So natural frequency of the system is very important in the analysis of the dynamic problem as to provide the information related to the dynamic characteristics of the system without external forces and any energy loss. Now, the vibration that takes place under the external exciting forces is called as force vibration. Now, when the excitation is oscillatory, the system is forced to vibrate at the exciting frequency. Now, if the frequency of excitation coincides with one of the natural frequency of the system, a condition of resonance is encountered and is dangerously large oscillating system, which may result in the failure of the system. Because theoretically, we'll be observing that the amplitude shoots to infinity when the impulse frequency coincides with the natural frequency of the system. Now, the force vibrating system will be vibrating initially in an unsteady manner till the transient state decays. And then the system will be vibrating in a steady state manner with the frequency equal to the exciting frequency. Now, let us see in the dynamic system how we try to write the equation of motion. As I said, it all depends upon the number of degrees of freedom. Depending upon the number of degrees of freedom, we'll be having so many number of equations. If the system is a single degree of freedom system, it has one equation. If it has 2 degrees of freedom, it will be having 2 equations. It will be multi-degree of freedom. It depends on the number of degrees of freedom. An n system will be having n equation. A continuous system which is having infinite degrees of freedom will be consisting of infinite equation. But one cannot solve all these infinite equations. So it is going to be restricted to the situations which all depends upon the application and the way in which the instruments are available for the measurements. So depending upon that, the restrictions about the number of frequencies and the number of equations are to be considered. And this is again going to be playing a key role in the analysis of any continuous systems in the software. Because it all depends upon how many equations you are going to consider for the solutions to make it as accurate as possible. So which, as we discussed, any dynamic system plays the key role, all depends on the mass and the stiffness. So the mass and the stiffness to what extent we consider for determining the dynamic characteristics of the system will depend upon the accuracy which is required. So many degrees of freedom has to be considered while analyzing it on the software. So where in the software it gives us the mode participation factor and the mass participation factor. Among this, the mass participation factor has to be taken into account, in which 90% and above of the mass participation factor has to be considered whenever we expect an accurate solution. Many times we see that even when the system is made to run the analysis for the higher modes up till 400 modes, but still we see that the mass participation factor is less than 60%. Then in such case, we have to run for more modes and see that the mass participation factor is more than 90%. So when the equation of motion has to be written, the basic vibration model of a simple oscillatory system consists of the mass and the stiffness. As we know from Hooke's law, the force is directly proportional to the displacement which causes, and the constant of proportionality is which we would define it as the stiffness. And this will cause certain internal energy, which we call it as the potential energy. And due to the movement of the mass, there is a certain amount of kinetic energy involved in the system. And thus the mass and the stiffness are going to be key in the description of the equation of motion. Now, the first step in solving the vibration problem is to setting up the differential equation of motion. Now, there are three approaches of setting up the differential of equation of motion. One is by applying the Newton's second law of motion, by using the D'Alembert's principle, or by using the energy principle. So any of these can be adopted to set up the differential equation of motion. Now, before we setting up the differential equation of motion, the first thing which we have to do is creating the mathematical model of the dynamic system and study about the free body diagram of the dynamic system, in which we show the complete information of the forces which are acting on the system. And knowing the forces which are acting on the system, then you apply the laws and principles to generate the equation of motion. Now, whenever there is an energy loss in the system, which we usually call it as a damping, this has to be considered so as to reduce the amplitude of motion. Because most of the systems which are going to be continuously running, in which when it is being excited, there is a certain region at which there is a variation, as in the case of in the initial stage of the starting. One cannot start directly to a higher level. It has to be gradually started. Similarly, one cannot stop any of the systems suddenly. It has to be gradually stopped. Now, during this stage, there is a variation in the frequencies. So when these frequencies are varied, we have to look into that these exciting frequency will never coincide with the natural frequency of the system to avoid the resonance, for which to control the amplitude, one has to provide some energy absorbers, which we call it as a damping. There are various type of damping associated in the engineering practice. First is the viscous damping, which is nothing but the lubricated sliding surface. Then the Coulomb damping or the dry friction damping, which is occurring due to the dry friction sliding of the surfaces. The structural or the exteriors of the solid damping, which is due to the internal friction and the molecule. Because we have seen in the materials when it is been subjected to the load, it causes certain stress. If these stresses are going to be beyond certain limit, that is beyond the yield stress, and again it is a reverse back, it will never trace the same stress strain path. There is an mysterious loop which is loss of energy. And that you call it as the structural or the series or the solid damping. Then interfacial damping or the slip, which is causing due to the interface of the contact surfaces, the roughness of the contact surfaces. Now, among all type of damping in mechanical engineering, most of the time we come across the viscous damping because that is being widely adopted in the industry. Now, let us study about the single degree of freedom system. So if you consider a simple spring mass dashpot system, which has been shown in the figure, having a mass M suspended by a spring of stiffness K and the dashpot having the viscous damping the C, and the spring and the dashpots are in parallel, then by the side of it, we have the free body diagram where the forces are being shown. So the inertia force is going to be in the direction of the displacement, whereas the resisting force due to the spring is opposing, and it is in the opposite direction to that of the displacement, which is equal to K into X. K is the stiffness of the spring. And the resistance in the damping is being given by C into X dot, because the damping force is directly proportional to the velocity. Thus, by Newton's second law of motion, we see that the summation of the forces in the direction should be equal to 0. Then we see the inertia force is acting in the downward direction, whereas the stiffness and the damping force are acting in the reverse direction. There is negative sign, and which can be rewritten as an equation as mx double dot plus cx dot plus kx equal to 0. Now, this is the equation of motion for a simple spring mass dashpot system of a single degree of freedom system. Now, you can see this equation is a second order linear homogeneous ordinary differential equation. for which we have the solution of it. But before going into the solution, we have a lot of things depending upon the type of damping present in it. We identify depending on the way in which the behavior of the system is going to be. And here we define what we call it as the damping factor or the damping ratio, which is nothing but the ratio of the actual damping to the critical damping. So the actual damping present in the system, whereas we define the critical damping as the system in which the system does not cause sustained oscillation. It performs only one oscillation and then comes back to its equilibrium position, where since it has a second order differential equation by converting into an algebraic equation by assuming the expression for the displacement x as e raised to the power of st. Now this is going to be converted to the time function. And then we see that it is going to be having a quadratic equation in terms of the displacement. Now the root of this quadratic equation will give you the solution. Now when the radical term, that means the square root term in the solutions, if that is being made equal to 0 and the corresponding value of the damping is called as the critical damping coefficient. Now based on the damping, we define three ways of the behavior. One you call it as over-damped system. The other one is critical damped system. The other one is under-damped system. Now, as I discussed, that the damping factor is defined as the actual damping to that of the critical damping zeta. And now expressing this and obtaining the solution, we have the amplitude x of t given by a e raised to the power of minus zeta minus root of zeta square minus 1 into omega nt plus of e raised to the power of minus zeta plus root of z square minus zeta square minus 1 of omega nt. Here omega n is the natural frequency of the system when damping is absent. And the constants A and B are evaluated based on the initial conditions of the system. For a specific case where all the three cases of damping which has been considered, so when zeta is greater than 1, that means the actual damping is greater than the critical damping. You call it as the overdamped system. And one can see the response of the overdamped system here. So it has going to a peak value and then decays exponentially. Now, when it is critically damped, it has a peak value only once and again decays back. There is no sustained oscillation. Whereas when zeta is less than 1, in which the actual damping is far, far less than the critical damping of the system, one can see there is a sustained oscillation. And even this, when we have used viscous damping, these sustained oscillations are in an exponentially decaying fashion. And we also define in the case of a dynamic system, the ratios of the two successive amplitudes in terms of the logarithm are going to have a constant value. And that we define it as the logarithmic decreminant. And this logarithmic decreminant is going to have a constant value for two successive amplitude, which is nothing but the logarithmic term of the ratio of the two successive amplitude. Now, when the external force is acting, so when the system once disturbed from its equilibrium position, executes the free vibration because of its own elastic properties, When there is no forces, the system returns to its equilibrium, depending upon the amount of damping present in it. In the previous case, for an under damped system, we can see that how much time it takes for decaying. Now, when the external force, in case of the forced vibrating system, this external impressed force acting on the system, which keeps continuously vibrating. Thus, it is very important for the designer to generate a mathematical model for the system which is being subjected to the forcing function and then analyze it. So in general, there are three types of forcing functions which commonly encountered in the engineering practice. The first is the periodic or the harmonic forcing function. That means its time period is going to be fixed, and the variations of this forcing function can be described by simple mathematical equations following certain law. And the second type of forcing function is an impulse forcing function. This impulse forcing function is going to be having a very high magnitude acting for a very short duration of time. And then whenever the forces are random in nature, we call it as the random forcing function. Let us see that when the forcing function is of a harmonic or a periodic forcing function, then the dynamic behavior is going to be studied based on the technique which determines the steady state response of a structure. We don't look about the transient state, because when the force is suddenly acted, initially it may be behaving transient, and then after a certain duration of time, it is going to have what you call as a steady state response. Thus, the general equation of motion which follows will all depend upon the force and the displacement. Now, these force and the displacements are also being assumed to be harmonic in nature, in which the forcing function F can be expressed as F naught of sine omega t and X as capital X sine omega t, where X is the amplitude of vibration and omega is the impulse frequency of the external forces. Now, considering a simple 1 degree of freedom spin mass dashpot system subjected to external force as shown in the figure. So, by again, for using the Newton's law of motion, all the forces which is going to be considered in the vertical displaced direction, which is going to give us mx double dot plus cx dot plus kx equal to f naught of sine omega t. Now, this is an equation of the force vibrating system. Now, this equation is a second order linear ordinary differential equation which is non-homogeneous. So the non-homogeneous equations are always been considered to be having two solutions. One you call it as the complementary solution, the other one you call it as a particular integral. Now the complementary solution is that solution which gives us the solution for the ordinary homogeneous differential equation, and the particular integral which gives the solution for the non-homogeneous equation. Thus, the solutions for the complementary solutions is nothing but as the free vibrating system. So the first term is going to be give us the transients response for the free vibrating system. The second term is going to give us the steady state response of the system. And this is the solution which is again being expressed in terms of the ratios of the frequency. So the frequency ratio, which is going to be the ratio of the impulse frequency to that of the natural frequency of the system. Now here you find the variations of the amplitude ratio, which is a non-dimensional parameter plotted against the frequency ratio. So when omega equal to omega n, that is when the value of this equal to 1, one can see that as the value of zeta decreases, the amplitude shoots to the maximum. And for an undamped system, that is when you make here zeta equal to 0, And omega, when omega by omega n equal to 1, and this becomes 0, and thereby the amplitude will be infinity. So to avoid this, the dampings are being provided. So with the damping, one can avoid the resonance conditions, and thereby the amplitudes can be controlled with the help of the damping. And the way in which the impulse frequency and the frequency phase, how exactly it's going to be varying, is also being plotted here for different values of the damping factors. Now here you can see that for the damping which is greater than 1, it does not have any peak. Now as the damping decreases, for the value of a specific value of for damping factor, there is a slight peak. As the value of damping factor decreases, the peak increases. Now, when there is a rotating unbalance, because in the previous case, which we considered is for a externally impressed force. Now, here it may be either due to the reciprocating or the rotating members, there may be causing certain unbalance in the force. And these unbalanced force are being taken into account and return the equation of motion, which is expressed as mx double dot plus kx plus k c dot x plus kx equal to me omega square sin omega t. And this me is what the eccentric mass effect. Now, similarly, for the reciprocating mass, similar kind of equations can be obtained. And again, this is same as that of the previous case in which the external the harmonic force is exciting, except that F naught is now replaced by me omega square. And thus the steady state solution is going to be me omega square divided by root of k minus m omega square the whole square plus c omega square. And the phase difference of the displacement of the forces are going to be tan inverse of c omega by k minus m omega square. Now again, considering the terms in terms of the ratios of the frequencies and expressing the damping in terms of damping factor, we have the amplitude ratio in a non-dimensional form written as mx by me equal to omega by omega n square divided by root of 1 minus omega by omega n whole square plus 2 zeta omega by omega n square. And the phase difference between the displacement and the forcing function, the external impulse forcing function given by tan inverse of 2 zeta omega by omega n divided by 1 minus omega by omega n square. Now, it is being plotted here. Again, you can see here in the previous case, when the external harmonic excitation is occurring, all curves are being starting at 1, the amplitude ratio as 1. Whereas whenever there is an unbalanced force, the amplitude starts from 0. Another case of forcing function is due to the support motion. So instead of the external force acting on the system, if there is support itself having certain motion, then one can clearly describe the dynamic behavior of the system, which is given by if the support is being harmonically excited by as y is equal to capital Y sin omega t, at which the mass of the system is going to have the displacement as harmonic, and that is going to be x sin omega t. And the equation of motion is going to be mx double dot plus cx dot plus kx equal to y cy dot plus ky. This again is going to be giving us two type of response. One is partially transient for a small duration of time, and then the steady state response. Usually the transient response is neglected. It is the steady state response which is going to give us the complete information. And for that, the steady state solution is given by the amplitude ratio of the support motion to that of the mass motion, that is x by y, is given by root of 1 plus Q zeta omega by omega and the whole square divided by 1 minus omega by omega and the whole square plus Q zeta omega by omega and square. And the phase difference between the displacements of the support and the mass is given by this expression. And here you can see again, the amplitude ratio is going to be starting from unity. And the frequency ratio is at this. Now one can observe in this case, all the curve is passing through a particular point where the value of omega by omega n is 1 by root 2. And the value of omega by omega n is 1 by root 2. We see that there is no displacement in the mass when it is excited at the base. Both the base and as well as the mass are going to be having the same displacement. Now, the same expression can also be used for what you call it as the transmissibility. A transmissibility is because due to the motion or due to the force. Now, in certain cases, specifically in the measuring instrument, we try to measure the amplitude, velocity, and acceleration, and for which we make use of this theory and try to see how exactly the information is being captured. Or if the force is transmitted to the foundation or to the machine, both things can be observed here. Based on this, one can look at the controlling, which is the parameter which has to be controlled for restricting of the motion or restricting of the forcing function. So here, whenever the value of omega by omega n is going to be less than 1 by root 2, less than 1 by root 2, one has to control the amplitude. And to control the amplitude, one has to look at the appropriate design of the damper. So the appropriate design of the damper has to be appropriately looked into that. And again, the mass of the system will also be playing the key. Because we know that the frequency is going to be stiffness by mass. So since the mass is going to be in the denominator term, as you reduce the mass, the stiffness increases. As you increase the mass, the frequency decreases. Whereas in the region, whenever the frequency ratio is greater than 1 by root 2, the damping does not play much of the role. It is the stiffness of the system which is going to be playing the key role in the behavior of the system. So these are the things which are to be looked upon. And now exactly how the vibration isolation has to be done. As just now we discussed, the isolations are the vibration absorbers which are placed between the vibrating system and the supporting structures. The isolating material may be pad of rubber, felt or cork or the metallic spring or the viscous damper. Now the effective of isolation may be measured in terms of the force or the motion transmitted to that in the existence. There are two types of isolation, that is force isolation or the motion isolation. That's why I told you transmissibility is the case of the force exciting system, which is defined as the ratio of the force transmitted to the foundation to that of the impressed force. So here again, the same system in which the transmissibility can be expressed as the ratio of the force transmitted to the system to that of the impressed force, and that is being given by this expression. And this again is going to be similar to that of the previous case. Thus, when the damping is negligible, the system can be treated as an undamped system in which the transmissibility is going to be equal to 1 divided by omega n square, the whole square minus 1. Thus, we see that when omega by omega n equal to 1, the transmissibility will also be shooting to infinity because it is going to be making the denominator term to be 0. So thus one has to be reduced. Now, where it can be observed that if the transfer T is to take place, the value of the frequency ratio omega by omega n should always be greater than √2. In an undamped system, from a static equilibrium conditions, we have that the mass, so that is the weight of the system, should be equal to the static deflection into the spring constant. Now, with this, one can define the omega as K by M equal to G by delta, or K by M is equal to omega square can be replaced by G by delta. So if you know the static deflection of the system, one can easily determine the frequency. So wherein the transmittivity ratio can be expressed as 1 by 2 pi f the whole square into delta by G minus of 1. Again, here the same thing, similar to the support motion. The transfer T is going to be completely absorbed. And we see that when omega by omega n is less than 2, the amplitudes are going to be higher, and the damping is what which is going to be concerned in the design. When omega by omega n is greater than √2, it is the spring which is going to be playing the key role in the design of this circuit. Thus, when a damping system are subjected to a sudden aperiodic function, as we discussed, that's the transient response. The response of the system is known as the transient response whenever it is subjected to a sudden loading, which is going to be temporarily sustained vibration, and then it decays out. The transient loading are also known as impact or the mechanical shock or a periodic excitation, which is characterized by a sudden or a severe application. In real life, mechanical shock is very common, like a free drop of an item from a height, or an automobile passing through a road bump, or a shock in a forging hammer, etc. Now, in analyzing the system for the transient loads force, it is necessary to idealize the forcing function. Now, the dynamic behavior of the system is manipulated and studied under the application of the forcing in a standardized manner by considering 4 types of typical test signals. One is the step, ramp, parabolic, and impulse. Apart from this, the conventional harmonic function, which is of sinusoidal signal, is also being considered. Now, unit step signal defines a sudden change in the properties of the actual signal, where it can be defined as R of t equal to A for time t equal to 0, greater than 0, and that is going to be equal to 0 for time t less than 0. When A is equal to 1, you call that to be as a unit step signal. Now, unit ramp signal is a constant rate of change in the input. There is gradual application of the input. The ramp signal defines the constant velocity attribute to the actual input signal. Now, this ramp signal R of t can be defined as A of t for t greater than 0, and this equal to 0 for t less than 0. When A equal to 1, we call that to be as unit ramp. That means it is going to be directly proportional. A parabolic signal gives us the second derivative, which is the acceleration distinction of the actual input signal. And this is defined by R of t equal to A t square by 2 for t greater than or equal to 0 and equal to 0 for t less than 0. Now, when A equal to 1, the parabolic signal is called as a unique parabolic signal, which is being commonly used for predicting the acceleration in the measuring equipments. And then we have an impulse. It's a force of a very high magnitude that acts for a short duration of time, but the time interval that is finite. Now, the impulse is the time integral of the force, and it is designated by the notation f prime. F prime has an integral of f of t into d theta. So dt is going to be for a small range. The figure shows an impulsive force magnitude of f prime by epsilon with the time duration of epsilon. There is for a small duration of epsilon we have. Now, when f of prime is equal to unity, such a forcing limiting case where epsilon tending to zero, that is here it is epsilon tending to zero is called as a unit impulse or called as delta function. Now, a delta function at t equal to z is defined by the symbol delta of t minus z and has the following properties. That is, delta of t minus z equal to 0 for all t except that at z. So at z for a small duration of time epsilon, the impulse force of a high magnitude is going to be acting. Now, if delta of t minus z is multiplied by any time function f of t as shown in this figure, now the product will give you 0 everywhere except at t equal to z. And its time integral is given by integral of f of t into delta t minus z into dt. And that is going to be equal to f of z for the value of z varying less than 0 and z for less than infinity. Now here, since f into dt is nothing but the force into the time, which is equal to the mass into velocity. So the impulse force acting on a mass will result in a sudden change in its velocity, which is equal to f prime by m. Because here dv by dt will be equal to f prime by m, which is an appreciable change in the displacement. Thus, for a damp free vibrating single degree of freedom spring mass dashpot system, we have considered the equation of motion here, in which the initial conditions at time t equal to 0, the displacement is 0, and at time t equal to 0, the velocity is what we expect. Now, the response of the spring mass dashpot system initially at rest and excited by an impulse f prime will have the initial condition x equal to 0 and x dot equal to f prime by m. Then the equation of motion here x dot is now replaced by f prime by m. And that is going to give us the expression for the response of the system. And thus this can be written as h of t equal to f prime into h of t, where h of t representing the exponential decaying of the system. That is f e of to the power of minus zeta omega n t divided by m omega n into root of 1 minus zeta square into sine of root of 1 minus zeta square omega n t. Now here root of 1 minus zeta square omega n is also called as the damped frequency. Now, if any arbitrary excitation is there, then one can consider that to be made up of many impulses. Now, if you consider one impulse, how exactly the response for this impulse is going to be, and then further it can be treated. Thus, we have some standard test signals for which the Laplace transform, because here we always try to study initially in the time domain and then convert it into the frequency domain. So when we talk about the frequency domain, it is always easier to consider the mathematical formulation. So thus the time domain, the differential equations in the time variables is now converted into the frequency domain by using the Laplace transformation, and then adopt the Laplace transformation method to solve this differential equation. Then take up the inverse Laplace transformation and convert it into the time domain back. So thus we'll be writing down certain expressions which is going to have the standard signal and the corresponding Laplace transformation converting the time domain to the frequency domain. So similarly, the random vibrating system can also be treated, in which most of the random analysis is being treated using the statistical techniques. And that's the reason in the solvers, that is in the software, we don't have the term random analysis. Instead of that, we call it as spectral density analysis. That is because using the statistical techniques, we try to find the mean, average, then the root mean square, root mean square, standard deviation, and then the spectral density, wherein a lot of group of data are being analyzed using the statistical methods and then try to solve. but the procedures are going to be similar to the same. Only thing is the methodology which is being adopted is by using the statistical technique. The dynamics problems which are being solved using the finite element technique. And the finite element techniques, as we adopt the energy method, so even in the dynamics using the energy method, Lagrangian has developed a methodology using the Hamilton principle. Now the same methodology is being adopted in the finite element method, in which the general treatment of the dynamic systems are formulated for the scalar quantities of kinetic energy, dissipating energy due to the resistance offered or damping or frictional energy, and the potential energy and the work potentials, which are developed due to the internal energy stored and the external work done. We consider usually that the kinetic energy expressed as T and the total potential pi, which consists of the potential energy and the work done, and the energy dissipation as R. So here first, considering an ideal system for a free vibrating system in which there is no external forces, but only due to the internal resistance, the system tends to vibrate, for which there is no energy loss. Now, when that is the case, we have only the kinetic and the total potential. The total potential, which again consists of the external work done and the internal strain energy stored. And by Hamilton principle, the Lagrangian has used the expression given by d by dt of dl by dqi dot minus dl by dqi plus del r by del qi dot equal to 0, where r is the dissipating energy. Now, for a body with a distributed mass, the kinetic energy is expressed as half into integral over the volume density rho into velocity square, that is displacement, the derivative square, which is expressed as half into integral over the volume rho dot to u dot square into dV. Similarly, the strain energy is expressed in terms of the stress and strain, which in turn is expressed in terms of the stiffness and the displacement. So now the work done is going to be due to the body force, traction force, concentrated force, and the moment. All these things considered to be when finite element formulation, which is being expressed in terms of the displacements. The kinetic energy is now going to be expressed as half into q dot transpose into me into q dot, where q dot is the velocity function. The strain energy is expressed as q transpose into ke into q, where q is the displacement, k is the stiffness, and the work potential is going to be force into displacement. Now, the total energy for the general elastic body are being obtained by summing up and assembling our work for the overall problem, where the total energy is being given to be half into capital Q transpose into K capital Q minus of Q transpose into F. Then the kinetic energy is half into Q dot transpose into M into Q dot, where M is going to be the mass matrix, K is going to be the stiffness matrix, F is going to be the external forcing function. Now, using the Lagrangian and then by adopting the Hamilton principle using the partial differential equation as expressed previously, one will finally arrive at the equation of motion as mx mq double dot plus kfq minus f equal to 0, or mq double dot plus k into q equal to f. This is the general equation of motion for a free vibrating system with the external forces. If external forces are absent, then we call it as free vibrating system, and it is undamped, for which case the equation of motion becomes m into q double dot plus k into q equal to 0. Now, for a damped system, the damping coefficient will be directly proportional to the velocity vector, hence c into q dot is incorporated. And when external force along with the damping is incorporated, then you have the equation to be solved in the finite element method as m into q double dot plus c into q dot plus k into q equal to m. And this is the equation of motion for a general damped force vibrating system. Here, depending upon whether this equation is going to be linearly varying, then you call it as a linear vibrating system. If these variations, that is, whether it may be mass or damping or force or stiffness or the displacements are going to be non-linearly varying, then you call it as non-linear vibrating system. Now, whenever the force which you are considering here is going to be acting for a very short duration of time, then you call that to be as a transient response. Or when the force is going to be harmonically applied continuously, then we call it as the harmonically steady state response. And when the forces are going to be random in nature, then we call that to be as a random vibrating analysis. But the equations is going to be the same. But how exactly the behavior of the variables are going to be depending upon this, the solution of this equation will be depending. For different variations, we have different types of solutions and different types of analysis are to be carried out. So among the dynamic analysis, the first one, that is when the system is free vibration without any external force and without any energy loss, is what is a compulsory thing which has to be carried out in almost all the software, which usually called as modal analysis, which gives us the information related to the natural frequency and the mode shape. So only then the further analysis can be carried out, whether it is nonlinear or transient response or is it random response. Now here I have taken a simple example of a cantilever beam for which we have the analytical solution. And the analytical solution is being expressed by using the hyperbolic and the cosine function. So the trigonometric functions is being identifying for the behavior of the system with respect to time, whereas the hyperbolic functions are being used for defining the geometric boundary conditions of the system. These are being evaluated in terms of the constant beta Ln. And these constants for the different boundary conditions are being specified for different modes. This is for the first mode, second mode, third and fourth modes are being generally expressed in almost all the textbook. Using this with the geometry and the moment of inertia and the Young's modulus and the density of the system and can predict the frequency. Substituting the values and predicting the frequency analytically. This is the fundamental frequency of the cantilever beam, which is 12.245, and this is second, and this is third and fourth. Now, using the finite element analysis, theoretically, this has been calculated and arrived at the stiffness matrix and the mass matrix, and then expressing that in the characteristic equation. Now, applying the loading and the boundary conditions, then treating the boundary conditions, eliminating the degrees of freedom and the boundaries, reduces the size of the matrix. Now, solving this equation, one will obtain what we call it as eigenvalues. These eigenvalues are nothing but the square of the frequencies. So these are the frequency for which theoretically we have seen that the frequency is this. Analytically also we have seen that the frequency, the first fundamental frequency is 12.245. But finite element method gives the value as 12.2489. And the second frequency is 121. And this is an approximate one because of using one-dimensional element. Now the same thing is being solved using the ANSYS software and determined that the first frequency is this value, that is 12.2289. And the mode is this. And the second one frequency, which is being found to be as 76.529, here also 76.629. The third frequency is 214.53, and here it is 214.682. So on the first four frequency period, analytically has been calculated, which is very well compared even with the one-dimensional analysis. Whereas if you try to go in for a three-dimensional analysis, one can determine the three-dimensional dynamic behavior of the system. And even in this, the results are being compared with the analytical solutions, which is being found to be coinciding to the exact values. Now one can see that one-dimensional analysis, the second mode was being given as 200 something. That is because it takes it only the translatory displacement, no rotational. Whereas in a three-dimensional case, here this you can see, observe that it is the twisting torsional mode of the cantilever beam. And that is going to be this. These are the higher mode frequencies which are being combined the mode, which has all the longitudinal, lateral, and as well as the twisting mode. Whereas this also has all the three mixed modes. Now, whenever we try to do in the practical situations, before doing the model analysis, one has to cross-check whether the results which are being obtained is accurate or not, for which initially perform a self-weight analysis. And in the self-weight analysis, check the reaction force, take the mass of this, and the standard acceleration which is being given. The gravity load, whatever which causes, will give you the reaction forces. First, compare these. The reaction force should be equal to that of the gravitational force. Once that is been compared, then you perform the analysis and do these calculations and verify the results. So this we have to analyze for one of the practical cases where the total mass was 455, acceleration due to gravity, and the reaction force which we obtained is 4364.3. From this, you calculate what is going to be the deflection. That is, you extract the deflection at the center of the mass of the system. And that is been found to be this. Now, using this, find the frequency. Whereas from the modal analysis, the first mode natural frequency was found to be 21.71. Whereas the calculated one with the values extracting the static deflection of the system is 20.1. It's almost very nearer. Once this has been made sure, then you further proceed with any other dynamic analysis. And even to arrive at these solutions, one has to look at what is the mass participation factor. The mass participation factor should be more than 90%. So this about the theoretical aspects. If you have any questions.
The Jagdish sir said to estimate the frequency of a component or the natural frequency, we need to first find what are the natural frequency by using the modal analysis. So we need to perform the modal analysis. Yeah, here by dragging drop the modal analysis here from the analysis system from the workbench, and then we need to insert the material details here in the engineering data, where you can insert your own material by typing your name and name of the material and inserting its property. And later on you need to import the geometry here, and then under model we need to set up the boundary conditions and loading. Here when we import the geometry, we will get two geometries here. I have created two uh, simple cubes to replicate the 2 degrees of freedom spring mass system, and I have connected the two springs. I have not modeled the actual springs here because when we model actual springs, it may get complicated while meshing. So we can represent the stiffness and the damping effect of the springs by using the connection group in ANSYS. If you are interested to analyze the spring st- stresses and the deformation. Then you need to design the spring. If not, you can insert the spring as a rigid model in connections. Then you need to check the material details under materials, and if you want any coordinate system to represent, you can insert the coordinate system here. And as I said, like in connections, you need to insert right click and springs. Here you get the springs and you need to input the details like here we consider this top of the spring is connected to some plates or some mounting. That mounting is not considered, so we consider it as the ground. So here we are mentioning it as body to ground in the scope. So only one scope is needed, which is as a scope mobile. Here we need to select this face, and we need to assign the stiffness value here, the longitudinal stiffness, and the same thing for the second spring between the two cubes. So here we need to give them as a scope between body to body, because here we are connecting two bodies with the help of the spring, and we need to mention the stiffness. After defining all these things, you need to mesh the component, and then you need to insert the displacement. Let's say you need to insert some displacement in the downward direction for these two components, which means the displacement is set to free only in y direction, so it can oscillate in only y direction to extract the first two mode frequencies, mode shape and the frequency. After inserting this, we can extract the maximum number of frequencies by defining the number of modes we need. Like I have inserted six, we can extract more than that. In the upcoming example, I'm going to show more than by inserting the number of frequency modes, how we can extract. And now we keep it to two or six, and then yeah, inserting the displacement. And here we are not going to define the boundary condition. Why? Because we are already defined here the spring as mounted some ground location here. So this point is going to act as a ground or some wall. So it will act as a boundary condition. Then we need to insert only the loading condition here, that is a displacement, and then solve it. After solving, we can get a deformation or the mode shapes. Under mode shapes, this will be the first mode. Like the both masses will oscillate in the same direction like this. And in the second mode, you can see they are in out of phase, like these two conditions. So which means this can be evaluated by the formula, in which the mass m1 with 0.981 kg and mass 2 with the same mass, and the stiffness we have inserted with the 200 Newton per meter, and the second mass with the 200 Newton per meter. And we have a formula to find angular frequency omega 1 and omega 2. And finding this omega 1 and omega 2, we are going to find the natural frequency. We know the formula, like 2 divide omega 1 divided by 2 pi. That is, we got with the hand calculation, we got f1 and f2. That is the first frequency and the second frequency. And the same frequency value we got from the ANSYS solution, that is 1.4 and 3.6. Here you can check here 1 point here 1.4 and 3.67 nearly equal to this example problem. And the next example is on the harmonic analysis. Under this harmonic analysis, and one more thing here, the participation factor, as Devi sir mentioned in the theory session, we have the mass of about 1.96 kgs. This is to be in some case, if they have if the client or the customer has not mentioned any frequency range, you can extract up to 90%. If they have mentioned the operating range frequency, we can extract up to the range. Let's say from 1 hertz to 1000 hertz, then we can extract only up to the 1000 hertz. If not, they have not mentioned, then we need to extract up to 90% of the participation factor. So we got in the effective mass of about 1.9. What is the total mass of 1.96? We got it in participation of effective mass, and in the same way, the ratio of the effective mass to the total mass we got in y direction is 1. Means the uh, complete mass is included in this modal analysis within the 6 modes of frequency. And for this bracket analysis, we can perform the frequency response, like for the applied load, how the geometry is going to behave under its mode shapes. So first we need to, yeah, the statics analysis is performed to know the reaction forces at the fixed location, and the modal analysis is performed to extract the natural frequency of the bracket, and the harmonic analysis is performed to extract the FRF, the frequency response from the system. Then here the static case is performed. And under the modal analysis, as I said, like first we need to insert the geometry in the space line here, and the same thing will be used for the remaining cases, the same engineering data and the meshing. Uh, due to time constraint, I'm not going to explain much into these options like material and the geometry. We can focus more on the simulation part. After inserting the material, that material will be seen in the material details. We have considered aluminum as the material here, and we need to assign the material in mounting bracket location in the material details assignment as aluminum. If you have any structural steel or stainless steel, by selecting those things, we can insert the material, and we need to mesh the component to capture the curvature. Some defeaturing options and the capture curvature options are being used to have the capturing of the curvatures. And then the modal analysis, we can extract up to 10 modes, which means up to 712 hertz. That is the maximum operating frequency. So we can restrict to it for 10 modes so that the computational time can be reduced. If you extract up to 90%, we are not going to operate in that frequency, then the remaining modes will be waste of time and also the computational time. So it's better to know what is the operating frequency range for this component so that we can extract up to the range of that frequency and the mode shape. Here I have in the modal analysis, we are not going to define any of the loading. We are only fixing the locations or giving the boundary conditions for the system. That is fixing these two holes of the bracket, and then I am going to perform the modal analysis. I have fixed here two phases, and then I given the input as maximum of 10 frequencies, and I have solved the problem, and I got the first mode of vibration here, going to oscillate in x direction, and the second one with some higher degrees of freedom, and the next one is in z direction, and the fourth one is with a twisting. Can increase the scale. This will be the true scale, and if you want to visualize better, you can increase the scale and you can visualize it. And the fourth mode, fifth mode, you can look into them. Later on, we need to perform the harmonic analysis. In the harmonic analysis, we need the mode shape results. So the solution of the modal analysis is connected as a setup file that is an input file for the harmonic analysis. Under harmonic analysis, we need to give the force that is going to operate sinusoidally. So how the system is going to behave for this load case. That is a force with minus 10 kilonewton in negative z direction. For that force, we need to extract the results, right click and solve it. Then you can see the total deformation here. This is you can see the changes, the phase, how it's going to change. At the beginning, you can see the range, like in the first frequency ranges at the beginning, and going to have a smaller amplitude. And as the frequency range increases, it starts to have the maximum amplitude of 2.5 that we can see in the response spectrum. That is how to extract this response spectrum is like selecting the point where you need interested location from where you want to extract the FR. Then select the phase response like deformation and evaluate all result. And the direction also important. Give the you can duplicate without result and you can change the X, Y, and Z direction. If I give the Y direction, let's see here. At the first mode here, this is a peak value where we are getting about 8 of deformation, which is nearly about 27, and the first mode of frequency is also 27, which means when you operate this bracket with a force of minus 10 kilonewton, at the first mode of frequency we are getting the response of maximum of 8 deformation here in the nearly at the first mode shape. This is how you need to extract the FRF frequency response, and then we can use some damping and those things to reduce the amplitude. And the next example is on the transient case and the random case. Here you can see the component is similar to a cantilever beam, but it's a arm of drone, drone arm. Then the same case, same here with defining the geometry, material, and then we need to mesh the component, and then we need to perform the modal analysis here. You can see here I am extracted up to 20 modes, more than enough for this case. It's up to 15 hertz, and the first frequency is with 77 hertz. When you operate it, it's a first mode, and the second mode in the horizontal direction, and the third mode, fourth mode, fifth mode is with a twisting. So when you apply some a twisting force on this uh, arm, it's going to have a maximum amplitude at the fifth mode frequency. So we need to check whether this load is capable to sustain by the component. And if you see the random vibration, in the random vibration we can give the input. Yeah, first we need to perform the modal analysis, and the results of the modal analysis is need to be connected to the random vibration. And then in the random vibration, we need to give the input in terms of PSD, that is G acceleration, that is G square per hertz, which we get these values from the standard which component you are performing. Like if you're performing any some railway or some aerospace part, then you need to refer those standards with respect to those field, and you need to get those standard, and we need to input these values. So these values will be directly available in the standards. Then inserting these values, we can solve the problem, and from that we can get where we get the maximum deformation and also the RMS value of the I have considered this vertex here, and I have inserted the response PSD. So I got this PSD for the range of the frequency we have operated. And in the transient case, here the shock analysis can be performed. Here I am going to insert the modal analysis as an input for the transient solution. Under the transient solution, here I am going to insert the acceleration condition. Here actually you can see three half sine waves, but actually it's a single half sine wave. Here I have deactivated these two sine waves, so it's showing in a blue color. And also you can see in the right side the values input. And first we need to input the analysis settings, like how many number of steps you are going to perform the simulation. That is 19 steps. Under the first step will be with a sub step of 4, and the step is going to end at some 1 e to the power of minus 3 seconds, milliseconds, that is 1 millisecond. And the second step will be the 2 millisecond, 3 millisecond, like that is going to vary up to the 18th step. And in the 19th step we are allowing the system to get a decay with amplitude with up to zero point 0.1 seconds with a substep of 320. So we have applied the acceleration of about from 0 to 9.8 e to the power of 5 mm per second square, and it's going to return back to 0, that is with one half sine wave. Then we are going to leave the system as it is. So how is going to decay the amplitude over the time period. And also we need to input the damping factor here, the damping ratio in the analysis system, damping ratio, so that if you not insert any damping value, the amplitude won't get decayed. When you insert the damping, due to the effect of the damping, it's going to decay. Then you can solve the solution, and under the total deformation you can see the maximum amplitude is going to about 8.7. Later on, due to the effect of damping, it is going to decrease its amplitude over the time period. And if you increase the time, and it's going to come at the maximum value is going to come reach to 0. If I play the animation, you can see the how it's going to decay. It's actually scaled model. I decrease the scaling or like this is how we can use the transient, random, and also the modal analysis for our frequency based simulations. These are the 4 examples I need to show in this webinar.